In this video, I'm going to show you a new formula for finding the sum of squares. And to make sense of this, I'm going to start actually by describing what it is that happened with the old formula, or the formula that you've already been introduced to. The sum of squares is, so far in my videos, been shown this way. It is the sum of the squared deviations. So the formula literally is what the name is. The sum of squared deviations, the sum of squares. What we're doing is we are summing up squared deviations. And so for that reason, because the formula tells us exactly what it is that we're working with here, this is called the definitional formula. It's the formula that you look to see what it is that's actually happening here. What if sum of squares equals to 8, what does that 8 mean? Where did the 8 come from? Well, the 8 is what happened when we summed up squared deviations. When we had a look at how far is each score from the mean, square those. Remember, we squared them to get away from having any negatives, cancel with positives, and give us a 0 as an answer. So we took our deviations from the mean, we squared them, and then we summed them up. Why did we sum them up? We sum them up because we're looking for an average deviation, or what my videos have shown so far, what we call a standard deviation. It's trying to be an average deviation. It's on average how much do scores deviate from the mean. Well, anytime you're going to take an average, you have to have a sum over the number of things that went into that sum. You have a total over the number of things that contribute to the total. So that's what an average is, or a standard. A standard deviation is like an average deviation. All right, so that's what we've done so far. The new formula that I'm introducing here is called the computational formula. Now, it's called a computational formula because it's a little bit easier to work with in terms of actually crunching numbers. If I have a big list of data, if I have a large sample, I might not want to have to go through and find every single deviation first and then square them and then sum them up. This formula is actually going to look a little bit worse. It seems like there's more going on here, but it's a little bit easier to work with when you have a lot of data. Okay, so this is the formula. This is what's called the computational formula. All right. I think the best way to illustrate this is to just show you both formulas being used side by side. So I'm going to set up some data here. Let's work with some values that we've been working with in some other examples. So I'm going to work with 48, with my data being 48, 49, 50, 51, and 52. You might recognize this from a previous concept video where I found that the total was equals to 250, and I used that total to find the mean. That is 250, or sorry, the sum of x over n, which is 250 over 5. My average is 50. So if I want to use the definitional formula, if I want to show you the definitional formula, the first thing that I do, considering that I have addition, that's what a summation sign is telling me to work with, I have brackets, I have subtraction, and I have an exponent. The first thing that I need to do is deal with the brackets, because order of operations, or BEDMAS, tells me I start with brackets and work my way through exponents, division, then multiplication, then addition, and finally subtraction. Now we have subtraction inside of our brackets, but because we have to do brackets first, I'm going to work out that subtraction in my first step dealing with this data. So I'm going to do 48, that's my first x, minus the mean, and the mean is 50. So 48 minus 50, that's negative 2. Then my next x, 49 minus 50, that's negative 1, and so on. So I've dealt with brackets. And incidentally, the subtraction, because it was in the brackets, I've dealt with that as well. Next comes exponents. So I have to take each one of these results, square them. All of this is stuff I've done in previous videos, so this is just sort of a recap of the definitional formula. I have to square each of these results. So negative 2 squared is 4, negative 1 squared is 1, and so on. And so that takes care of my exponents. There is no division, there's no multiplication, but there is addition. So that's the last thing that I do. I have to add these up. And so when you add them up, you get 4 plus 1 is 5, plus 1 is 6, plus 4 is 10. So I've now summed my squared deviations. And that gives me 10. So my sum of squares is 10. So that's done. But what if I do the computational formula? Well, I'll start with the same data. But imagine that I hadn't done anything yet. I just had my data. Last time, I had to add up all of my data. The sum of x is 250. Do I need to do that again? Yes. I do need the sum of x. You can see it's right here. There's the sum of x. So I work out that the sum of x is equals to 250. Now the last time, I used that to find the mean, because I needed the mean to find deviations. When I'm dealing with a computational formula, though, I don't need to find a deviation. I don't need to find the mean. It doesn't exist in the formula at all, so I'm not going to bother with that. In fact, the only thing that I need, or the only things that I need, are the sum of x, which I've already done. I need n. Well, n is simple. It's just 1, 2, 3, 4, 5 different values, so I know that n is equals to 5. And finally, I need to know the sum of x squared. Well, now this one you have to be careful about. Just like up here where we did order of operations to figure out which order to perform all these operations in, when I have the sum of x squared, I've got two things going on. I've got summation, that's addition. Sorry, I guess I should call that, don't want to confuse it with subtraction, so I'll call that A for addition. That's what summation is. And then I've got an exponent going on there. If I'm looking at order of operations, there's no brackets, but there is an exponent, so that's going to come next, or that's going to come first. So I have to square each x. So I have to do 48 squared, and then 49 squared, and then 50 squared, and so on. So 48 squared is 2,304. 49 squared is 2,401. 50 squared is 2,500. 51 squared is 2,601. And 52 squared is 2,704. Now, I don't just need x squared. We've done the exponents. We need to now take care of the other operation here. We need addition. We need to add these up. That'll give me the sum of x squared. And when you add up all 5 of these values, it comes out to be exactly 12,510. Now what I can do is I can plug each of these values. I've got my sum of x squared worked out. I've got my sum of x worked out, which I can square, and I've got n. So I'm going to work all of these into the formula. Sum of squares equals to the sum of x squared. That one is 12,510 minus the sum of x in brackets, which is 250. Square that and divide by n, which is 5. So let's do the fraction first. This is 250 squared is 62,500, and we're going to divide that by 5, and so this ends up being 12,510 minus this fraction. When you work this out, it comes out to be 12,000 even, And so we end up getting, 12,500. Let me correct that here. And so the answer ends up being 10. So the sum of squares is 10. This is the same as what we got when we did the definitional formula. Over here on this side of the squiggly line, we have the computational. Now remember what I said was that the computational is used, or its reason for existing is to allow you to do less work. When we were dealing with the definitional formula, we had to work with our raw data, then we had to find deviations, then we needed a third column to square the deviations. With computational, also actually we had to work out the mean. With computational, we had our raw data, which we added up, but we didn't have to find the mean, and we didn't find deviations. We just had one other column, and then we jumped right into substituting things into our sum of squares formula. So it was a little bit less work. We only had 5 data points though. If we had a lot of data, if we had 100 data points or 1,000 data points or something like that, it would have been a lot less work to use the computational formula. So this formula, this second formula, let me just put these side by side again. The definitional formula is sum of squares is equals to the sum of the squared deviations from the mean, and the computational is the sum of squares is equals to the sum of x squared minus the sum of x in brackets squared over n. These two formulas will always produce the same result. If you are more comfortable with using one over the other, then go ahead, unless they specifically say use the computational formula to figure this out, but I doubt they're going to do anything like that. So you can use whichever one makes you more comfortable. They both will always give the same answers regardless. It makes no difference which one you use. However, the computational is a little bit easier when you have more than a few data points. So you might want to get used to dealing with this one or used to using this one. Having said that though, if you just prefer this one and want to stick with it and forget about the computational altogether, you could probably get away with that too. Again, except for a situation where they specifically ask you to show that you understand how to do the computational formula, but I doubt that that's going to arise. So that's it. 2 different formulas. You can take your pick of which one you want to use. You're going to see a lot of that in statistics. A lot of times students would ask me which one is the correct one to use. If there are 2 formulas that give you the same quantity, there is no correct one to use. It's just whichever one you feel like using. They both give the same answer.